How did the universe begin? Or how everything came into existence? Well, there are many theories that explains us how the universe began. One such theory is the Big Bang theory. It gives us an idea of how the universe began. The Big Bang theory is the leading explanation for how the universe began. Simply put, it says the universe as we know it started with an infinitely hot and dense single point that inflated and stretched, first at unimaginable speeds, and then at a more measurable rate, over the next 13.7 billion years to the still expanding cosmos that we know today. Here's the theory. In the first 1043 seconds of its existence, the universe was very compact, less than a million billion billionth the size of a single atom. It's thought that at such an incomprehensibly dense, energetic state, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were forged into a single force, but our current theories haven't yet figured out how a single, unified force would work. To pull this off, we'd need to know how gravity works on the subatomic scale, but we currently don't. It's also thought that the extremely close quarters allowed the universe's very first particles to mix, mingle, and settle into roughly the same temperature. Then, in an unimaginably small fraction of a second, all that matter and energy expanded outward more or less evenly, with tiny variations provided by fluctuations on the quantum scale. That model of breakneck expansion, called inflation, may explain why the universe has such an even temperature and distribution of matter. After inflation, the universe continued to expand but at a much slower rate. It's still unclear what exactly powered inflation. Aftermath of cosmic inflation. As time passed and matter cooled, more diverse kinds of particles began to form, and they eventually condensed into the stars and galaxies of our present universe. By the time the universe was a billionth of a second old, the universe had cooled down enough for the four fundamental forces to separate from one another. The universe's fundamental particles also formed. It was still so hot, though, that these particles hadn't yet assembled into many of the subatomic particles we have today, such as the proton. As the universe kept expanding, this piping hot primordial soup, called the quark-gluon plasma, continued to cool. Some particle colliders, such as CERN's Large Hadron Collider, are powerful enough to recreate the quark-gluon plasma. From the first stars to today, there wasn't a single star in the universe until about 180 million years after the Big Bang. It took that long for gravity to gather clouds of hydrogen and forge them into stars. Many physicists think that vast clouds of dark matter, a still unknown material that outweighs visible matter by more than 5 to 1, provided a gravitational scaffold for the first galaxies and stars. Once the universe's first stars ignited, the light they unleashed packed enough punch to once again strip electrons from neutral atoms, a key chapter of the universe called reionization. Scientists have tried to glimpse this cosmic dawn, but the results have been mixed. Back in 2018, an Australian team announced detected signs of the first stars forming around 180 million years after the Big Bang, though other groups haven't been able to recreate their results. By 300 million years after the Big Bang, the first galaxies were born. In the billions of years since, stars, galaxies, and clusters of galaxies have formed and reformed, eventually yielding our home galaxy, the Milky Way, and our cosmic home, the Solar System. Even now the universe is expanding. To astronomers' surprise, the pace of expansion is accelerating. Estimates of the expansion rate vary, but data from the James Webb Space Telescope adds to a growing body of evidence that it's significantly faster than it should be. Radiation in the early universe was so intense that colliding photons could form pairs of particles made of matter and antimatter, which is like regular matter in every way except with the opposite electrical charge. It's thought that the early universe contained equal amounts of matter and antimatter. But as the universe cooled, photons no longer packed enough punch to make matter-antimatter pairs. So like an extreme game of musical chairs, many particles of matter and antimatter paired off and annihilated one another. Somehow, some excess matter survived, and it's now the stuff that people, planets, and galaxies are made of. Our existence is a clear sign that the laws of nature treat matter and antimatter slightly differently. Researchers have experimentally observed this rule imbalance, called CP violation, in action. physicists are still trying to figure out exactly how matter won out in the early universe. A tiny, ghostly particle called a neutrino and its antimatter counterpart, an antineutrino, could shed some light on the matter, and two big experiments, called Dune and Hyperkamiokande, are using these chargeless, nearly massless particles to try to solve the mystery. Has the Big Bang theory been proven? This isn't really a statement that we can make in general. The best we can do is say that there is strong evidence for the Big Bang theory and that every test we throw at it comes back in support of the theory. Mathematicians prove things, but scientists can only say that the evidence supports a theory with some degree of confidence that is always less than 100%. So, a short answer to a slightly different question is that all of the observational evidence that we've gathered is consistent with the predictions of the Big Bang theory. The three most important observations are: 1. The Hubble law shows that distant objects are receding from us at a rate proportional to their distance, which occurs when there is uniform expansion in all directions. This implies a history where everything was closer together. 2. The properties of the cosmic microwave background radiation, CMB. This shows that the universe went through a transition from an ionized gas, a plasma, and a neutral gas. Such a transition implies a hot, dense early universe that cooled as it expanded. This transition happened after about 400,000 years following the Big Bang. 3. The relative abundances of light elements, He4, He3, Li7, and deuterium. These were formed during the era of Big Bang nucleosynthesis, BBN, in the first few minutes after the Big Bang. Their abundances show that the universe was really hot and really dense in the past, as opposed to the conditions when the CMB was formed, which was just regular hot and dense. There's about a factor of 1,000,000 difference in temperature between when BBN occurred and when the CMB occurred. That's all for this video. Let us meet in the next video. Thank you for watching.